Welcome to the lesson on section 10.4, Exponential Growth and Decay. In this lesson, we'll look at examples of how to use differential equations to model population growth, radioactive decay, and heating and cooling of substances. First, we'll look at a model for population growth. Most of the population growth models you learn about in Algebra 2 and Pre-Calc follow the assumption that the rate of population increase is directly proportional to the current population. Let's use this assumption to write an initial value problem describing the growth of a population and then solve the problem. For a population y with initial value y0, I'll call the rate of increase of the population dy dx, where x is time. To make it proportional to the population at time x, I'll set dy dx equal to a constant k times the current population y. Separate by dividing by y and multiplying by dx, and integrate both sides. An antiderivative of dy over y is the natural log of y, and the antiderivative of k is kx. Add a constant c to one of these sides to generalize our solution for the indefinite integral. Rewriting this in exponential form, I get y equals e to the kx plus c. And recall from the previous lesson on solving separable equations that we can rewrite this as a constant a multiplied by e to the kx. Substituting my initial condition that when x equals 0, y equals y0, I find that the constant a is equal to y0. So the solution to this initial value problem is y equals y0 times e to the kx. In example 1, we'll use the exponential growth model we just found to solve the following problem. The half-life of carbon-14 is approximately 5,730 years. In 1988, the Vatican consented to give a few fibers from the Shroud of Turin to scientists to carbon date. Scientists found these fibers had 92% of the original carbon-14 left. What do these findings imply about the age of the shroud? Using the exponential growth model from the previous slide, substitute an initial value of 1 representing 100%, 1/2 representing an ending amount of 50% after 5,730 years have passed. Solve this equation for the constant k. Taking the natural log of both sides, the natural log of 1/2 is equal to 5,730 years times k, and k equals the natural log of 1/2 divided by 5,730. Now that I have the value of k, I'll use it to find out how much time must pass before 92% of the carbon-14 remains. Substitute 0.92 for our ending amount, 1 for the initial amount, and the natural log of 1/2 over 5,730 for k, and solve for t. Taking the log of both sides, t is equal to the natural log of 0.92 divided by the value of k, or approximately 689 years. According to these results, the shroud is approximately 689 years old. For more information on the Shroud of Turin or on carbon dating, you can do a quick Google search. Now on to heating and cooling. Newton's law of cooling states that the rate at which the temperature of a cooling object decreases is proportional to the difference between the temperature of the object and the temperature of the surrounding environment. Newton's law of heating says something similar for the rate at which the temperature of a heating object increases. In my next example, a cup of water with initial temperature 95 degrees Celsius is placed in a room with temperature 21 degrees Celsius. A, assuming Newton's law of cooling applies, set up and solve an initial value problem whose solution is the temperature of the water t minutes after it's placed in the room. B, how many minutes will it take for the water to reach a temperature of 51 degrees Celsius if it cools to 85 degrees Celsius in 1 minute? I'll use capital T for temperature in degrees Celsius and lowercase t for time in minutes. If dt is the rate at which the temperature of the water decreases, then it's equal to a constant K times the difference between the temperature of the water, capital T, and the temperature of the room, which is a constant 21 degrees Celsius. Separate by multiplying and dividing, and integrate both sides. Convert to exponential form, and rewrite e to the kt plus c as a times e to the kt. The initial temperature of the water is 95 degrees at time 0. Substitute these values into the equation and solve for a. A equals 74. It's important for you to note that the value of the constant a does not come out to the initial temperature here. It's common for students to make this assumption, but that assumption would be incorrect for heating and cooling problems. Do you know what a really represents? It's actually the initial difference in temperatures between the water and the room. With the information given so far, we find that the relationship between time and temperature is capital T minus 21 equals 74 e to the k lowercase t. We need more information before we can find the value of lowercase k. For part B, the water temperature is 85 degrees after 1 minute. Substitute these values for capital T and lowercase t and solve for k. K is equal to the natural log of 64 divided by 74. Now use the value of K to find the time it will take for the water to reach a temperature of 51 degrees. It will take about 6.2 minutes for the water to cool to 51 degrees. This concludes the lesson on section 10.4, Exponential Growth and Decay.